Okay, so let's look at this example here. So when we're dealing with bigger matrices, ones that are obviously bigger than 3 by 3s, then the row reduction becomes even more important. And you can, the determinants go quickly. Okay, so if we look at this here, now if I want to eliminate this one, right, I'm going to take negative row 3 plus row 4, and so what I'm going to get is this. Right, so these two determinants should be equal. Now, then what I can do is I can swap this row and this row, and I'll have it in my echelon form. So let's do that. Now I'm going to pull out a negative sign because I'm swapping rows. Remember, every time you swap rows, changes the sign. So now it's going to be negative of the determinant of this. And so now, if I look at the diagonal, it's going to be, the determinant is going to be equal to negative of negative 5, which is just 5. Now, so this example raises an important point. So this chapter's introduction, so we were gives the formula for 2 by 2s, 3 by 3 determinants. So we know that they exist, but not for determinant functions of matrices that are 4 by 4 or bigger. Okay. Instead, definition that we gave, definition 1, gives properties that a determinant function should have and leads to computing determinants by Gauss's method. Okay. Instead of memorizing the formulas, we just use Gauss's method and use the properties to figure it out. Let's see here. Now, however, for any matrix, we can reduce it to echelon form by Gauss's method in multiple ways. Okay, so remember, we've talked about that where there's different ways, different roadmaps of getting to echelon form. For example, given a reduction, we could change it by inserting the first step. That multiplies the top row by 2, and then the second step that multiplies it by 1/2. So we have to worry about what 2 different Gauss's method reductions could lead to 2 different computed values for the determinant. So that's what we have to worry about. Will that happen? Okay. Now, so first we show that if there is such a function, then there is no more than 1. Okay, so we have to show that there's no more than 1. And the example above illustrates, this example here illustrates the idea. So we got 5 by following the properties of the definition. So while we have not yet proved that that determinant of 4 by 4 exists, that there is a function with properties 1 through 4, if such a function satisfying them does exist, then we know what value it gives on the above matrix. So we know that it has to, that it gives 5. Okay, so we're going to introduce another lemma, and then we'll go from there.